The moon. We hit the moon, and it kept vibrating, not metaphorically. When astronauts left scientific instruments on the lunar surface during the Apollo program, they weren't just planting flags. They were installing seismometers, devices designed to detect ground motion. Later, when spent rocket stages were deliberately crashed into the moon's surface, something unexpected happened. The moon didn't just shake. It rang for minutes, sometimes for over an hour. On Earth, a large impact produces seismic waves that scatter, dampen, and fade relatively quickly. Earthquakes spike, oscillate, and then settle. The moon behaved differently. It vibrated like a struck tuning fork. To understand why that was surprising, we need to understand how earthquakes work. On Earth, when tectonic plates shift or when an impact occurs, energy travels through the planet as seismic waves. There are primary waves, P waves, that compress and expand material, and secondary waves, S waves, that shear side to side. As these waves travel, they lose energy. Earth's interior is layered: crust, mantle, outer core, inner core, with materials of varying density and temperature. The mantle is partially plastic. The outer core is liquid. These layers absorb, scatter, and dampen seismic energy. Friction converts motion into heat. Water in cracks and porous rock absorbs energy. Irregularities disrupt wave coherence. The planet is messy, so the shaking fades. The moon is not messy in the same way. When the NASA Apollo missions deployed seismometers between 1969 and 1972, they created the first lunar seismic network. These instruments recorded several kinds of moonquakes. Deep moonquakes caused by tidal stresses from Earth's gravity. Thermal quakes caused by temperature changes at sunrise. Shallow quakes. Meteorite impacts. And then there were the artificial impacts. When the Apollo 12 mission's Saturn V third stage was crashed into the moon in 1969. Seismometers recorded reverberations that lasted nearly an hour. The Apollo 13 impact stage rang for even longer. The data showed a slow build-up of oscillation, like a bell being struck and then humming long after the initial strike. It was dramatic, and it led to speculation. Was the moon hollow? No, but it was clearly different. Clue 1. Dryness. The moon is extremely dry compared to Earth. There is very little water within its interior. Water in rock acts as a damping agent. It absorbs vibrational energy and helps dissipate it. Without water, seismic waves can travel farther with less attenuation. Dry rock behaves more elastically. The moon's interior lacks the lubricated fractures and fluid-filled pockets that dampen Earth's vibrations. Less damping means longer ringing. Clue 2. Fractured crust. The moon's crust has been heavily bombarded for billions of years. Unlike Earth, it lacks plate tectonics and erosion to recycle and smooth its surface. The outer layers of the moon are highly fractured and broken, a structure known as megaregolith. This fractured structure can trap seismic energy, causing waves to scatter and reverberate within the crust. Instead of dissipating cleanly, energy becomes trapped in a complex network of cracks. The effect is similar to sound, echoing within a cavernous structure. Energy lingers. Clue 3. Internal structure. The moon is smaller and cooler than Earth. It does not have a large, fully liquid outer core like Earth's. Its internal layers are more rigid overall. Seismic modeling suggests the moon does possess a small core, likely partially molten, but the majority of its interior behaves more like a solid elastic body. Elastic bodies transmit vibrations efficiently. With fewer energy-absorbing layers, waves can reflect internally for extended periods. So when the moon is struck, the energy doesn't vanish quickly. It reverberates. The Apollo Lunar Surface Experiments Package, ALSEP, recorded years of seismic data. These instruments revealed that deep moonquakes often occurred at regular intervals tied to the moon's orbital position, caused by tidal forces exerted by Earth. The moon flexes slightly under Earth's gravity. Even without atmosphere or tectonic plates, it is not static. It is active but quietly, but its seismic signature is unique. Where Earth absorbs and forgets, the moon resonates and remembers. The phrase "rang like a bell" became popular shorthand. But it doesn't mean the moon is hollow. It means its internal properties differ significantly from Earth's. Low water content, extensive fracturing, high elasticity, different thermal structure. These combine to create long-lived vibrations. If Earth were as dry and rigid, it might behave similarly. The moon is not empty, it is simply less damped. Yet the mystery remains subtle. We only measured the near side extensively. The Apollo seismometers were clustered in specific regions. We have models of the moon's interior, crust thickness variations, mantle composition, small metallic core, but there are uncertainties. How uniform is the mantle? How extensive are deep fractures? How does temperature vary with depth? Seismology remains one of the best tools for probing planetary interiors without drilling. When a body vibrates, it reveals itself. The moon told us something unexpected. Not hollow, just different. But how different is its interior, really? If we placed a new global network of seismometers on the moon today, higher precision, wider distribution, what would we learn? The moon rang like a bell, and perhaps it still does. We just aren't listening anymore.